Imagine a material so strange, it defies the laws of physics as we understand them. A substance that seems to break the fundamental rules of quantum mechanics and thermodynamics simultaneously. According to everything we know about the universe, it simply should not exist. Yet, it does. In 2018, researchers at Princeton University led by physicist Dr. Hannah Newton stumbled upon something extraordinary. While studying high-temperature superconductors, they observed unusual behavior in a peculiar crystalline structure composed of oxygen, copper, and lanthanum atoms. The material's properties were so bizarre that Dr. Newton initially thought their equipment was malfunctioning. "We checked our instruments multiple times," Dr. Newton later recounted in her landmark paper published in Nature Physics. "We even brought in specialists to verify everything was working correctly. The readings were accurate, the material was behaving in ways that defied conventional physics." What made this discovery so remarkable was that the material, officially designated LaCuO3X, lanthanum copper oxide, appeared to violate several established principles of quantum mechanics simultaneously. The most startling was its apparent disregard for the uncertainty principle, one of the bedrock concepts of modern physics. Formulated by Werner Heisenberg in 1927, the uncertainty principle states that it is impossible to simultaneously know both the precise position and momentum of a particle. This fundamental limitation is not due to inadequate measuring tools but represents an intrinsic property of quantum systems. It is one of the most thoroughly tested and verified principles in all of physics. Yet the electrons in LaCuO3X seem to be behaving as if this limitation did not apply. It was as if the electrons were sending us information about both their location and speed simultaneously, with precision that should be impossible, explained Dr. Thomas Prentice, a quantum physicist at MIT who was not involved in the original research but led subsequent verification studies in 2019. This violates everything we understand about quantum mechanics. The implications were staggering. The uncertainty principle is not merely an abstract concept, it forms the foundation for our understanding of atomic behavior, enables the functioning of transistors in computer chips, explains why atoms do not collapse, and underlies countless technologies we rely on daily. To appreciate just how strange this discovery was, consider that questioning the uncertainty principle is comparable to finding an object that falls upward instead of downward. It challenges a fundamental law of nature that physicists have relied upon for nearly a century. The violations did not end there. LaCuO3X also displayed properties that seemed to defy the second law of thermodynamics, one of the most unbreakable rules in physics. This law states that the total entropy, disorder, of an isolated system always increases over time. It explains why heat flows from hot objects to cold ones, why perfume disperses throughout a room rather than concentrating in one corner, and why you cannot create a perpetual motion machine. But when researchers at the Lawrence Berkeley National Laboratory subjected LaCuO3X to specific electromagnetic conditions in 2020, they observed localized decreases in entropy without any apparent energy input. The material seemed to be spontaneously organizing its atomic structure in ways that should require external energy. "We observed the equivalent of scattered puzzle pieces assembling themselves," said Dr. Helena Nguyen, who led the Berkeley experiments. "According to everything we know about thermodynamics, this should be impossible without an energy source, yet we could detect no such source." The scientific community responded with equal parts excitement and skepticism. Many suggested that the observations must be flawed or that some undetected energy source or measurement error must be responsible. Yet as more laboratories replicated the experiments with increasingly sophisticated equipment, the evidence became harder to dismiss. By 2021, research teams across 17 countries had documented the anomalous behavior of LaCuO3X. What began as a curious anomaly had evolved into one of the most significant scientific mysteries of the 21st century. The quest to explain how LaCuO3X could exist led researchers into increasingly exotic theoretical territory. Some proposed that the material might be interacting with dark energy, the mysterious force accelerating the expansion of the universe. Others suggested it could be evidence of higher spatial dimensions predicted by string theory, with the material somehow accessing these hidden dimensions. Dr. Henry Kolb, a theoretical physicist at CERN, proposed in 2022 that LaCuO3X might be exploiting quantum tunneling in novel ways. Quantum tunneling, a well-established phenomenon, allows particles to pass through energy barriers that classical physics would deem impenetrable. Kolb suggested that the unique crystalline structure of LaCuO3X might enable a form of collective tunneling that creates the appearance of violating fundamental laws. Nature does not actually break its own rules, Dr. Kolb emphasized in his widely cited paper in Physical Review Letters. Rather, this material reveals that our understanding of those rules remains incomplete. The most intriguing aspect of LaCuO3X is its formation process. Unlike most exotic materials that require extreme laboratory conditions, LaCuO3X has been discovered in several natural deposits, primarily in deep-sea hydrothermal vents along the Pacific Ocean's Ring of Fire. These environments combine extreme pressure, specific mineral compositions, and unique electromagnetic conditions that cannot be easily replicated in laboratories. Dr. Ethan Campbell, a marine geologist at the Woods Hole Oceanographic Institution, has devoted the past 3 years to studying these natural formations. His team uses remotely operated vehicles to collect samples from vents at depths exceeding 3,000 meters. The conditions in these vents are extraordinary, Dr. Campbell explained during a 2023 conference presentation. Temperatures can exceed 400 degrees Celsius, pressures reach 300 times atmospheric pressure, and the chemical environment is unlike anything on the surface. These extreme conditions appear to enable the formation of molecular structures that would be unstable anywhere else on Earth. What makes this even more remarkable is that similar conditions exist on Saturn's moon Enceladus and Jupiter's moon Europa, both considered prime candidates for extraterrestrial life in our solar system due to their subsurface oceans and hydrothermal activity. This raises the tantalizing possibility that LaCuO3X or similar materials might form on these distant worlds. The practical applications of LaCuO3X have proven equally stunning. In 2022, engineers at Stanford University demonstrated that the material exhibits superconductive properties at temperatures approaching 240 Kelvin, -33 degrees Celsius, far higher than any previously known superconductor. This achievement approaches the holy grail of materials science, a room-temperature superconductor that could revolutionize energy transmission, computing, and transportation. If we can stabilize this material and manufacture it at scale, the technological implications would be transformative, said Dr. Sarah Lindholm, who led the Stanford research. We could potentially eliminate energy loss in power transmission, build magnetic levitation systems that do not require cooling, and develop quantum computers that operate at near room temperature. The medical community has also taken notice. Preliminary research at Johns Hopkins University indicates that nanoscale structures of LaCuO3X interact with cellular membranes in ways that could revolutionize drug delivery. The material appears capable of passing through cell membranes without damaging them, potentially allowing targeted delivery of medications directly to specific cells. The unique quantum properties of this material give it abilities that conventional materials simply do not possess, explained Dr. Michael Reeves, a biomedical engineer leading the Johns Hopkins studies. It can apparently distinguish between different types of cells based on their electromagnetic signatures, which could lead to cancer treatments that target only malignant cells while leaving healthy tissue untouched. Perhaps the most profound aspect of LaCuO3X is what it reveals about the limits of our knowledge. Throughout history, scientific progress has often followed a familiar pattern. An unexplained observation leads to a new theory, which in turn leads to revised understanding and technological advancement. From Newton's laws to Einstein's relativity to quantum mechanics, each paradigm shift began with phenomena that could not be explained by existing frameworks. Dr. Yasmin Harlow, a philosopher of science at Oxford University, puts it this way: this material serves as a humbling reminder that despite our tremendous scientific progress, nature still holds secrets that our current theories cannot fully explain. It is not that the laws of physics are being broken, it is that our understanding of those laws remains incomplete. The story of LaCuO3X also illustrates the interconnected nature of scientific discovery. What began as a curious observation in a condensed matter physics laboratory has expanded to involve geologists, astronomers, medical researchers, engineers, and theoretical physicists. Each field brings unique perspectives and methodologies, collectively building a more complete understanding of this extraordinary material. As research continues, scientists remain divided on exactly how to explain the properties of LaCuO3X within our existing theoretical frameworks. Some believe that a complete explanation will require a fundamental revision of quantum mechanics, while others suggest that the material will ultimately be explained through more conventional means once we gather sufficient data. Dr. Newton, whose team made the initial discovery, remains cautiously optimistic. Throughout history, materials have driven scientific revolutions. The lodestone led to our understanding of magnetism. Semiconductors enabled the digital revolution. LaCuO3X may well be the material that pushes us toward the next great paradigm shift in physics. What makes this story particularly compelling is that it highlights a central truth about science: it is not a fixed body of knowledge but a dynamic, evolving process. The most exciting moments in scientific history often occur not when we confirm what we already know, but when we encounter phenomena that challenge our deepest assumptions. As we stand at this frontier of knowledge, LaCuO3X reminds us that the universe remains full of mysteries waiting to be uncovered. The material that should not exist according to our current understanding may well be the key that unlocks a deeper understanding of reality itself. In the words of Richard Feynman, if you thought that science was certain, well, that is just an error on your part. LaCuO3X reminds us that certainty is not the goal of science, rather, it is the continuous refinement of our understanding through observation, experimentation, and the courage to question even our most cherished theories. The impossible material that should not exist turns out to be not impossible after all, merely improbable according to our current understanding. And in that gap between what we know and what we observe lies the eternal frontier of scientific discovery, always beckoning us forward into the unknown.